Cool. Thank you for coming. My name is Nitsan. I'm going to talk to you about out-of-memory errors and how they happen, how you can stop them from happening, a little bit about JVM memory and so on. We'll do the bio slide very quickly. I work as a JVM developer for a company that does not want to be mentioned. I'm the lead developer on JCTools, which is like a concurrency library that a lot of people use. You're probably using it without knowing it because it's in Netty, and everybody uses Netty. I used to blog. Honestly, it was probably more than 5 years ago since I published anything, but it was a blog once. And I speak at conferences, again, on occasion, not that often these days. Throughout this presentation, there will be things with stars. The stars are like, you should remember this because it's starred. So important things will have stars on them. Inspirational quote with a star, just as an example for this. So you can remember that if you want. Right, so we'll be kind of breaking the memory hierarchy of the JVM from the top to the bottom, and then at the end we'll summarize everything. But essentially, the JVM is a process, and then it has internal stuff, and then what do we do about it? The important thing to always ask yourself whenever you have a setting or a limit on anything is what could possibly go wrong. And the thing that goes wrong with memory is that you run out often. The JVM is a bit more challenging because we tend to think about the nice fluffy Java allocation mental model where we allocate objects and somebody takes care of it, and we forget that it comes with all the luggage that everything else comes with. So to start off with, the JVM is just another process. So we're going to talk about process memory just quickly. I hope everybody knows what a process is and that it has memory. Who knows what memory is? All right, the rest of you are in the wrong room. So every process needs to ask the OS for memory. So it takes pages from the operating system, and then it uses them. If you want a breakdown of all the pages, all the memory regions that your application is using, you can use proc maps to get that. The JVM finally exposes resident set size, RSS, as part of JFR now. So you can look to one more piece of information in your JFR files. And the key points, again, we're going to go through this quickly. The key points to remember about OS memory and process memory. When you allocate memory in C, or just in the olden days, and you don't use it, nothing happens. It's not part of your RSS. Only once you start touching it does it come into memory. So you can use always pre-touch as an option to force the heap into resident memory. I find that is, so people use it in latency-sensitive applications because they don't want the memory to come in late in the lifetime. I recommend people use it because it prevents surprises. So you start your application, you think you have memory, you use the heap, and then eventually it touches too much, and you end up running out of memory as a surprise 3 hours in or a day in. So I would suggest you use that all the time. ZGC does weird things with memory. In particular, it remaps the heap 3 times. And so if you look at RSS with a JVM running ZGC, you'll have a nasty surprise. So just be ready for that. And the final thing that kind of catches people with this, if you use malloc in C and you free and you think I've given back the memory, everybody else can use it, that's not the case. Malloc is sitting between you and the operating system. It has its own pooling mechanisms. And so when you give it back the memory, it assumes you're going to need it back very soon, and so it keeps it around. So this is not how things work. So it doesn't go back to the operating system. The JVM can return memory to the operating system. That's a recent-ish development, especially malloc trim is recent. It kind of always could return pages to the OS from GC, so from the heap. It is better about this now. So it does it if your application is idle. It'll try and return some pages to the OS. But I'm not a fan of uncommit because, like I said, if your JVM thinks it can use this memory later and it's not going to be around, then you're going to have a nasty surprise when you try and use it. malloc trim, on the other hand, is a very good feature that we saw a lot of success with because essentially it asks malloc to return OS pages to the OS, so memory pages to the OS, if they're not used. You can set this interval for malloc to run, and by default, it's not going to do it. So the default is 0, never do it. If you set it to something like once an hour, you're probably going to see a nice tapering effect on your RSS, where the JVM will return some of the allocated memory to the OS every once in a while. So that's been a huge help to a lot of services at the company that shall not be named. You can also trigger this manually. So very quickly, when you run out of memory, your process gets killed or your container gets killed. Sometimes even the OS will just restart. There's not that much that I'm not going to go into the details of when any of these things happen. You can look it up online. What I would highlight is that if your container dies for any reason, I would suggest you look into it. Don't just leave it to kind of die and restart, die and restart, die and restart in the background. Have a look. These things are quite wasteful and they're usually solvable. They indicate an issue. Right, JVM, which is what we care about a little bit more than the top level as Java developers. The JVM has a ton of mini regions inside it that are used for different purposes. And you can run out on any one of those levels. So you could run out of heap, you can run out of managed code space, and so on. So there's more regions than this, but this is the kind of essential breakdown. We'll go a little bit into each one of them. To have a view of how these regions are being used and how much you have to still use, how much is being used by the application, you can use NMT, native memory tracking. I can't remember when it came in, but it's pretty much in 11 plus. I think in 8 as well, but I'm not sure. You need to enable it on startup. There is some overhead, but most applications don't really register the overhead, so it's probably fine. The only kind of major pitfall with NMT is that it doesn't report RSS. So we're going to look at what it does report, but it can be quite confusing when you see something that is reserved or committed and it doesn't match your RSS experience. So you can use JCMD to pop out NMT stats. You can get them as JFR events. You can get it on JMX, but yeah, JMX sucks, so I wouldn't use it. NMT output, when you use any one of these things, will come out looking something like this. So you'll have reserved bits and malloc bits and committed bits. So let's just explain them away. So reserved means whatever we set aside for the region. If you have a region that can resize, like the heap, you've set a minimum amount for the initial bit and then it can grow up to maximum, then it'll reserve the minimum, and then when it hits it, it'll grow. So reserved doesn't necessarily mean maximum. Committed means the JVM has let some bits of itself use this region. So either it's code blobs in the code cache, or objects, or on the heap, or other. The relationship with the heap is maybe a bit more complicated. So yeah, the more you commit is the more you've given away to the application. You will notice that the larger regions use mmap rather than malloc. The general advice in the kind of native world is if you can manage your own memory and you need large chunks of memory, you're going to use mmap. If you're just allocating small bits, you're going to use malloc. So that's why that breakdown is there. The interface with RSS can be quite confusing because if you use a region in the JVM. You've taken something out and then you put it back again. So let's say you've compiled the method, but then you drop that compilation, so the code blob is no longer in the code cache. Essentially, it's no longer committed. But because the JVM touched that page and hasn't let it go back to the OS, that uncommitted piece of memory is still impacting your RSS. And also, if you've committed to a certain chunk of memory, but nobody touched that memory, it's not going to show in RSS. So looking at NMT and trying to deduce what happens with your RSS can be very confusing. There is a feature coming in 22-23 from Thomas Joof. Thomas used to be with the SAP team, and they had lots of nice features for memory tracking. I think he's now with Amazon, and a lot of these features are coming upstream, so that's very nice. So yeah, that's going to be useful, because currently you need to kind of take an MT, you need to take your proc maps and try and marry them together, and that's very unpleasant. How does this fall apart? So just a reminder that if never catch out-of-memory error, that's really stupid. But generally speaking, Java applications can't handle out-of-memory error. They should all have this flag on. You always want to exit when you run out of memory, because you're probably in some uncertain halfway baked state. You can either exit or you can crash. If you want a core dump, you can dump your heap, but just make sure you kill that JVM. So there's several flavors of the out-of-memory error for heap. So if you get one of those, you've probably leaked some memory or allocated too much or done something wrong. We'll get back to the heap just now. You can run out of metaspace, which tends to happen when you've set a limit on metaspace and then you run up against it, so just remove your limit. Keep an eye on it. Maybe you have a class loader leak or something of that sort, so you can look at JFR, you can look at the class loading log to track that down. There's more out-of-memory error type exceptions you can get, so you can look at this page for more inspiration. Stack overflow error is, you don't have a flag to kill your JVM for this. You should, because you can't handle that one either. So watch out for those ones. I think it might get logged in your JVM warnings, not 100% on that. You can set a diagnostics flag to make your JVM die when that happens. If it happens, you can increase the stack size. You can stop recursing so much. That's also good. This can be a little bit confusing because the default is 1 megabyte on Linux and it's 2 megabytes on Mac OS. So you can have something that works on your Mac OS laptop and then you put it on Linux and it falls apart. So that's why you see different behaviors, and you might have to set that flag. Sorry, it's not on the slide, that's XSS. Finally, your code cache might get full. This is something we've seen people hit when they upgrade their Java, so they move from Java 11 to 17. Compilation profile changes a bit, maybe inline is deeper, and then you end up with more code, and you run out of code cache. Now, my opinion, it should kill your JVM, because running in a crippled state where your compiler can't work is probably not what you want. It will print a warning. Who's printing GC logs? Anybody tracking GC logs in production? Okay. The rest of you, please gather GC logs. Anybody monitoring those GC logs for warnings? Or do you just use them for GC? Right. I don't know why people don't look at JVM warnings. Please look at JVM warnings. They are very instructive. They're not like, your typical application will dump a ton of warnings on you. When the JVM tells you it's in trouble, it is in trouble. So very worthwhile. You can split them into another file and just really monitor that one. If you have more than 0 JVM warnings, you probably need to look into it. There is a JFR event for code cache full, so you can try and collect that and monitor that. If you have a way to automatically monitor your JFRs, that might be a solution for you. Actually, sorry, one last thing. Yeah, there is a flag to trigger exit. It's only in developer mode, so maybe it can be upgraded to product mode in OpenJDK. Maybe that'll happen. Right. A lot of people deploy JVMs in container. Are you deploying in a container? Anybody? The rest of you are also deploying in a container and too lazy to put up your hands. So that's okay. I don't mind. Right. You have, generally speaking, kind of a Goldilocks dilemma. You want to have the porridge that's just right, but you don't quite know, so you over-allocate or you under-allocate. If you under-allocate, you'll get killed. If you over-allocate, you're wasting money. So you got to pick your poison. So you need to know how large the JVM is going to be. You're only going to find that out by monitoring, so monitor your JVMs. I'm just going to run through a few hot takes from seeing people and abuse the JVM in a container environment. So take those homes and do what you will. If you're running micro containers, if your container is weaker than your phone, maybe you've gone too far on the micromizing of your service. So just consider that. The smaller the JVM, the higher the overall fixed overheads that come with it. So if you're running like 1 gigabyte type JVMs, the overheads can add up very quickly to like 25, 50% on top of that. So you're not getting the best deal. If you can, merge a few JVMs and get a, larger container going, that's the way forward maybe. Larger JVMs benefit from large pages. Not a lot of people use that. I'm not sure why. It's not available in all container environment. Really depends on where you're running. So try and pick one that lets you use it because it's an easy win for a lot of Java applications. JVMs are not good about dynamic resources. So if you say, oh, I have 3 CPUs, but sometimes I have 10 CPUs, the JVM is going to pick one of those numbers, and that's going to be the number of CPUs. That's the number of CPUs it'll let everybody else, like writing Java, know that you have. And so the easiest thing is to use the same number for your request and limit for memory and for CPU. And unless you're like super sure about what you're doing, that's how you should use it. Fractional CPUs are not really working very well with JVMs. And the JVM is, depending on the version, but as a general rule, not that sure how many CPUs you have. So it's not very good about detecting CPUs inside a container. Set the active processor count explicitly and tell it how many CPUs you have. Otherwise, you get throttled because it's using more CPU than you've let it have. There's more hot takes. The RAM percentage thing, it was sold as like, oh, you'll deploy in all sorts of environments and you'll just say, I want to use 50% of the memory and that's going to be great. No, it doesn't actually work that well. I suggest you just script the sizing of your JVM to match your deployments. Probably have several categories of containers you deploy and make sure you fit well there. So you set the XMS, you set the XMX, set them to the same thing because you're the only one running inside that container, so it doesn't really make sense to try and grow and shrink. And like I said, request limit thing, just keep it the same. Keep it simple, it'll probably work out better. Always pre-touch, life will be less confusing, you'll have less explosions late in the game. The max direct memory size, that is the limit that the JVM puts on something like allocate direct, and Netty uses it and so on. The default is that it's the same size as the heap. That is probably too much for most applications. I usually tell people to set it to 128 because it's a random number that seems right and it works for most applications. Maybe your application needs more, you're going to have to find out. But for most applications, you don't really need that much, and leaving that number open leaves the door open to running out of memory and getting killed. finally, we have Alina here. Talk to her about Growl if you want to do like AOT compilation of your JVMs because you're running on something that is weaker than a Raspberry Pi. I'm not sure why you're doing that, but if you are doing that, talk to Alina and consider ahead of time compilation of your Java code. Okay, that's halfway through, 29 minutes. We're good. It's like slides are going quickly. Okay, direct memory. Direct memory comes in several flavors. People use direct memory because they like living on the edge, and also they want to take, either they're using the direct memory to do I/O, and then they need direct memory to talk to the OS, or they've tried to take their heap memory off heap because they've had GC issues. Either way, direct memory is limited by the max direct memory limit, which we've discussed. You can look at NMT and see how much of that has been used. There's a JMX bean for tracking byte buffer usage. You can try and use that too, but JMX is disgusting, so I don't know why you would. If you allocate direct memory, by default, the JVM is going to try and collect it later at a time of its choosing. It really sucks. For most applications, this is going to end badly, which is why people use Netty and why people steal the cleaner object out of direct byte buffer and just trigger the free themselves. If you're not doing that and you're playing with direct byte buffers, you're probably going to have problems at some point, because when you hit the direct memory limit, the JVM is going to try and do a full GC to see if it can find any dead direct byte buffers and get their memory back. It's going to be a mess. So yeah, probably don't do this unless you're stealing the cleaner directly, and then you know what you're doing, maybe. I don't know. Alternatively, you know what you're doing, you can use unsafe, which is what the JVM uses to allocate memory. You allocate, you free, and if you don't, you leak, but you know what you're doing. So that's fine, you're not even limited by the max direct memory size. There are no limitations, but you still get accounting from NMT, which is nice. Okay. This is a new thing. It's now in 22 as a product option. You have the foreign function and memory API. You can do nice things like try with resources, with a memory region. It's awesome. We're not going to get into it, but that's the future. This is where direct memory is going on the JVM. So when we use direct memory, we use malloc. Not just the JVM. You do direct allocate, you get malloc. And so the malloc heap is called the native heap, because terminology, they had to call it something. Malloc uses its own set of arenas because it manages memory. There's, by default, tons of arenas, like as many arenas as your CPUs multiplied by some amount. Every arena will get used by a thread, and then it'll allocate and free. You touch a little bit of memory, you end up with a shitload of arenas everywhere. It's supposed to reduce contention. The thing is, you're writing a Java application, there is no contention. You're not using direct memory that much. If you're using direct memory allocation repeatedly from lots of threads, you have problems, my friend. It's not the right thing to do. Stop doing that. Use Netty or something along those lines. And so you can probably reduce the malloc arena max to something like 4 and save yourself a ton of memory just like that. So that's worth trying out if you're trying to reduce the RSS of your process. It might cause contention because you're doing direct allocate from lots of threads, but then you know what you're doing, right? Okay. Remember, again, if you free, that doesn't go back to the OS. And remember that you can trigger malloc trim on a timer, on an interval, and that's probably going to save you a ton of memory as well. I mentioned Netty before. I work with Norman Mara on, at that employer that will remain unnamed. Netty is a massive piece of the Java ecosystem. Everybody uses Netty. Usually, if you look at a Java process, it uses netty at least once, probably 5 times in different flavors from different places. So netty implements its own pooled allocator, which is essentially its own kind of malloc implementation. The max memory is derived from the JVM setting, but you get the same kind of problems. So when you release into the netty pool, it doesn't release into malloc because you're going to use that memory again, right? And we want to be efficient and we want to avoid contention, so we have lots of arenas. And because you're using netty, and does anybody set the number of threads netty uses on the command line or otherwise? Nobody does. Because if you have netty, by default it will allocate as many threads as you have cores times 2, and then if you have 5 shades of netty in your application, then you multiply that by 5, and they all have their own memory arenas, and it's awesome. So you can set the number of direct arenas. Watch out for shades of netty. So you have your S3 SDK client, and you have your Cassandra client, and you have your Memcache client, your metrics client, all those clients. Clients, by definition, they probably need 1 thread, but they're using multiply of your cores, and they all have their own package names because they've shaded netty into them, and so you need to take this setting and rename it according to where they shaded it. Great fun. Yeah, try and not have shades of netty. It'll reduce the amount of resources you use. Chris West and Norman are working on integrating a new allocator into netty 4.2, I believe, which when it comes out, by default will not use up so much of your memory and will try and kind of protect you from this behavior. Other allocations. So you use a funky JNI library. It allocates memory. The JVM has no idea that it's happening. In fact, the JVM doesn't even know when it's allocating memory to unzip a file because nobody bothered implementing that tracking. So if you call into JNI and it allocates memory, NMT doesn't know about it, so it's not going to be accounted. So you still have to monitor the OS level RSS, then NMT, and then you'll have a gap, and the gap is what's not tracked. The best solution at the moment for profiling retained native memory allocations is a feature branch of Async Profiler. I met with Andrei Pangan this week, and he says it's probably going to get merged as a feature, probably in 3 or 4 or 5 months. So eventually it'll be there. Right now you have to build this from the branch and do it yourself. But then you get all the allocations with stack traces of where they come from and how much retained native memory you have, which is fantastic. So if you're trying to track down who is allocating all this direct memory in my Java code or outside of my Java code, that is the way to go. Finally, the familiar and the where we do most of our damage, the heap. There was a talk by Jarrett like 2 days ago about GC. I hope we have no overlap. I did not have time to see his slides, but I don't think we have overlap. Must have been a great talk. I don't know. Java heap is why we use Java for the most part. It was like the biggest thing about Java. You can write once, run everywhere, not manage your own memory. So you can always malloc, you never have to free. It's all just happening in the background for you. And heaps, traditionally on server-side applications, dominate everything else. So you would have a 64 gigabyte heap and change for code cache and all the other crap. So the heap is where the big money is for a lot of Java applications. We're going to do a quick run on GC terminology because I find it can be confusing. So, very quickly, live references means references that go all the way from a GC root to a reference. We're not going to talk about like soft references and weak references and all that crap because that's for an advanced class. But right now, If it's connected to a route, it's alive. Okay? If it's not alive, it's garbage. The live set is everything you need to run your application. There's like different life cycles, and you get like typical contents of a heap. So you get like your cached values, they will live forever. Your classes will live forever. Your connections will come and go, but maybe connections are long-lived and requests are short-lived, and so on and so forth. When you are done using a piece of memory, it goes into the great beyond. If you never release anything, you will run out of memory. So, I love this about Java because it denotes some kind of attitude to human beings, but you start new and young, and then you tenure, because everybody's an academic, and then finally you're old, and then you're garbage. That's life for you, right? We're all going in that direction. So allocation rate, important metric for any GC. The allocation rate is how much do we allocate at a given interval, usually per second. So 100 megabytes, 500 megabytes, gigabytes per second, depending on your application. Not only new allocates, also like when you use certain syntactic sugars like lambdas, like for loops, you allocate new and exciting objects. Sometimes they get eliminated by the JVM, most of the time they're not. The goal of GC, people forget this, is to seamlessly take care of memory, okay? And seamless in two senses. One is the Java sense, you know, it's programmatically seamless, I don't need to worry about, so it just happens for me. But the other seamless is the operationally seamless. So the application does not crash, and it does not produce overheads that are unpleasant to me. And these come in three flavors. So the more memory we use, the more money we have to spend, so that's cost. The more CPU the GC is using, it affects cost, but it also affects my application throughput, because if the GC is running concurrent to my application, it's eating up my CPUs that I would be using for my business logic, converting strings into more strings. And then you have pauses, which is where a lot of the literature is obsessed with, but you have latencies. If your application stops for 50 seconds to clean up, that can be unpleasant to your customers. The live set and the allocation rate kind of define the GC behavior. So we need so much memory for what's alive at any given moment, and then we allocate. And when we allocate and allocate and allocate, after a certain amount of time, because of the allocation rate, however much memory we can allocate before we run out of memory, and then we have to collect. Once the heap is full, you have to collect. Hopefully you do it before it's full. So those two numbers, your live set and your allocation rate, they are key to any decision you're going to make about garbage collection. So if you don't know those numbers for your application, try and find out. That was the refresher. So quickly, how do we size the heap? We have an expected workload that determines the live set and allocation rate. Things come in, we have things that are live, connections and so on. Application has to limit the workload, otherwise it dies, right? If you need 100 megabytes per connection and I give you 1 billion connections, you will run out of memory and die. And then this, by the way, will become how you limit the workload by killing your JVM. Usually it happens before that. You limit concurrency by other means. Okay, you just get so slow, people go elsewhere. Old gen, in generational GCs, but we're kind of making broad strokes here. Old gen has to be large enough to hold your live set. Okay. The young gen defines how often will you have to run GC, because you allocate, you run out of the young gen and then you collect. So the larger it is, the less times you're going to hit the GC cycle. And the young GC will clear most of the short-lived objects, but not all of them, because they're going to straddle the boundary. There's going to be some request that is ongoing during your GC cycle, so it'll stay alive. And that's why we have tenuring. Okay? You need to size your young GC to minimize the tenuring, okay, so that not so many objects make it into old-gen, and so you have to do less old GCs. Okay? So the more you tenure, the faster your GC rate will go, your old GC. So something like this formula is going to happen. All of this becomes more complicated with concurrent GCs, absolutely, but those are the basics that you need to have in your head when you're thinking about GC. So, simplified example, we allocate 100 megabytes, the live set is 1 gigabyte, so we tenure maybe 20 megabytes every time we do a GC, and then something is beeping. I'll just keep going, never mind. Right. If the heap size is 2 gigabytes, we're going to have a certain frequency of collections. Okay. If this is going to end up something like this, the point is, if we keep the allocation rate going, we're going to have a young GC every 4 seconds. Eventually, we're going to have an old GC every 100 seconds because we tenure so much garbage. The same application with more heap will, if it has less tenuring because we increase the heap size, we'll have to have less young gens because we have a larger young gen size, and it'll have less old gen because A, we have a bigger old gen, but also we're tenuring less. And so that's going to end up, with a young GC every 15 seconds and an old GC every, 3/4 of an hour or something like that. Okay, so that's in broad strokes how these things add up to cost you in your GC budget. And so to save money on GC and have smaller heaps, we have to optimize footprint. That comes in 2 flavors. We need to reduce the allocation rate, because when we have a low allocation rate, we have less young GCs, we have less CPU usage, we need a smaller young gen, we reduce the tenuring rate, and then we do less old GCs. Just generally, we don't need as much heap if we don't allocate as much. So that's great. You can observe allocations, profile allocations. I gave a talk at GeeCON Prague about allocation profiling 5 years ago or so look it up if it's still somewhere on the internet. You can profile with async profiler or JFR, and you can, because a lot of applications allocate an awful lot, you can limit the sampling, and then your profile won't be like gigabytes, it'll be smaller and more manageable. So that's good to keep in mind if you're doing allocation profiling. Common solutions to allocation problems. Very quickly, it's like reduce, reuse, recycle. There's like different flavors of this, but there's common issues. One of the most common is string format. People use string format where they can concatenate strings, or they can just avoid strings altogether. So try and do that. It'll always show up on your allocation profile. Choose efficient types where you can. Avoid allocations that you don't need, like composing a huge message that's going to go into the debug log, but you're not actually logging the debug level. Again, very common. So all of these things hold true for allocation rate. Reducing the live set, similar reasons. We need to reduce all GCs. If we can reduce all GCs, we don't have to have such a large heap anymore potentially. Sorry, if we reduce the live set, there's less to hold. All gen can be smaller. Finding out what the live set is tricky on concurrent GCs. It's a bit simpler on the old GCs. You can kind of estimate it if you look at your GC graph and see what the heap is like most of the time after GCs, but it's not 100% accurate. The only accurate way to know what the live set is to take a heap dump. It's going to interrupt your application, and analyzing heap dumps is unpleasant, but that's the only way to actually know what's there. Reducing the live set comes down to very similar bag of tricks. The main kind of trade-off here is where you use object pools or caches to reduce allocation, you're actually increasing the live set. So you need to pick your poison on that one and see what's meaningful. So a couple of tips here are, a lot of applications have hash maps and hash sets that are kind of small, and we'll see an example of how expensive that is. You can use flatter versions of that. Agrona is one good place to get it, but there's others. If you take a heap dump of almost every Java service, you will see a disruptor that log4j uses. By default, that's like 100 megabytes of your live set go to that, even though you're probably not logging that much. So you can size that to be 1/10 of the size. Your application will be fine, and you've saved a chunk of live set. A question that we all get asked from time to time: how big is an object? It's actually complicated because it depends on the JVM, the mode it's running, and so on. Size of the heap sometimes, which GC you're using. Don't worry about it. You can use JOL, which is an OpenJDK project, to print out the layout and the size of a given object. So we're going to do just that. This is both examples are real-world examples. Both of them are actually from Cassandra. Cassandra likes to take stuff off the disk and then break them up into tons and tons of little byte buffers. So let's say I have BB, it's a byte buffer, and we break it up into fields, and every value in the field is its own byte buffer. So it looks something like this. We use slice, so we're using the same backing array, so everything is great. The byte buffer, even though the backing data is 128 bytes, if you look, even the array has something like 10% overheads, because an array is also an object. It also has an object header. It has a length. And so 128 bytes become 144 bytes. And then on top of that, we've allocated the byte buffer to hold the array. That's another 48 bytes. And we end up paying for 128 bytes of data, 192 bytes. So that's quite the inflation. But now we wanted to break it down into fields. And now we're paying 992 bytes for 128 bytes of data. So I would love to say that this is obtuse, but this is actually much worse in reality. So yeah, wrapping things and having all these structures costs you. And if you try and kind of control those costs, you're going to have to tackle these problems. You can come chat to me later if you want to discuss some of the techniques. Another one that is really traumatic one, you can put flags in sets, and initially you say that and you think, oh, a set for flags, I can do like contains and intersect and all those kind of funky things you do with collections, and it's really nice and idiomatic. So you put all your flags in a hash set. And then it turns out that putting 64 flags into a hash set is like 5.7 Ks of memory. The alternative, like in that particular example, this was where the flags were coming from. They came from a long with 64 flags, 64 bits in a long, and it was 8 bytes. So we went from 8 bytes to 5.7 K. There are big savings to be had when you do these sort of things. Just have a look at your heap dump and find them. Summary, and I know I had to shrink the font to make it fit, but it's really almost everything on one slide. So Remember to find things that go out of memory and die, and find out why. Monitor your warnings, all of them. Keep your containers simple. All the options are here. Look at your native memory use, especially, netty is a common kind of culprit in Java applications. And the malloc fragmentation is also another one. Profile, heap dump, and be merry. And that is everything. We have 4 minutes for a Q&A, and let's see if that's going to happen. Does this work? No, it doesn't work. Okay. How do I get the slidey thing to... Okay. I feel this was not well thought out.
I can show you your room's questions if you want.
Yep.
Oh, you got it. Good.
I think so. So where's... Oh, yeah, killing my Wi-Fi was not the best. Okay, here's the XMS. My experience is, yes, it is still valid in 2024. I'm not sure what you mean by memory fragmentation. Is that like the huge pages issue, or is this like a container scheduler issue? So I'm not sure I understand that one. But yeah, if you don't set them as the same thing in a container, you're going to have fluctuating memory consumption. And then if you're super clever and you can work that out and your container scheduler is okay with that, great. But for a lot of applications, that ends up being a surprising behavior where your container gets killed because you've exceeded your request and there's not enough to give you up to your limit, and then you're not sure what happened. Why do we want to return memory to the OS? The experience I've seen with malloc is that you can cap your RSS growth by returning the memory to the OS. Technically, you shouldn't have to do it because you will reuse it, but I guess malloc is quite greedy. You can also switch malloc with another allocator, and then maybe you'll have a better time of that. Why should one exit when code cache is full? Functionality, okay. So the application is going to potentially get so slow because anything that gets de-optimized is going to go back into the interpreter that you're going to get paged about this. So that's my experience. Somebody's going to come calling for that application. And most service owners would rather that instance was dead than super slow. And then you can look at your JVM warnings, because you're monitoring them now, and change a flag, redeploy, and everything will be better. As opposed to having silently slow applications in production, which you can choose to do that, but that's not, I think, where most people want to be. Always pre-touch. Help against OS memory fragmentation. So I have to admit, I haven't heard as OS memory fragmentation as an issue. What I see people struggle with is they try and understand their RSS, they haven't set always pre-touch, and then the heap is 8 gigabytes, the RSS is 1 gigabyte, but it keeps growing because you keep working your way through the heap and touching it, and life becomes a bit more complicated. But also in a container environment, potentially you're just going to explode later, so I'd rather you explode it early. Why is JMX disgusting? well, coding it is disgusting, and then using it isn't that great either, in my opinion. The way I prefer to look at applications and the way I think the JVM kind of ecosystem is going is JFR, which is a much more flexible pipeline of data to use. Currently, if you want to plug to it as kind of a live source of data, it can be a bit challenging, but I think that's the way things are going. How to sanitize heap them from prod secrets. I don't know. I would guess there's some tools you can use. This is why a lot of companies have their own JVM teams, so that they don't need to ship heap dumps outside of the company. How to visualize NMT numbers. So you can take them from whichever source you get them and plug them into your metric system. We use like some export from JMX into the internal metric system. We have some kind of dashboards built on top of Java Mission Control. Pick your poison, really. Will you share your presentation? I will. That's it. Thank you very much.